Last week's class was I had to cancel it at the last minute. I hope nobody was stranded here. But anyway, we'll carry on from here, and we'll still have plenty of time to cover things. All right, so let's start with Chapter 2 and then do the buffer overflow project, which is really at the heart of understanding this stuff. So, a deeper dive into C. We'll talk about various features of C. So, one issue is scope. So the way programs are designed in C, you have the libraries included at the top, then you have global variables. Well, these are function prototypes, pardon me. These determine your functions. That's why they have these parentheses and parameters. And this is the return value is going to be integer. And here you define global variables. If you just define a variable up here outside any method, this variable will be shared by all the methods. And programmers that care about efficiency don't like global variables. They slow down the program, but they're very useful purposes. So you have some variable in C everywhere. Then inside main, you have local variables. Those will only exist inside main. And when main stops, they'll be gone. Of course, when main stops, everything will be gone. But if this was a subroutine that you could leave and come back, these variables would only exist inside the subroutine. This was shared among every routine. So you can have a function with two parameters, and here you have a local variable. So you pass in n1 and n2, and then it uses a local variable called val to perform some calculation, and it'll return the larger of those two numbers. Val is n1, but if n2 is bigger, val is n2, then return val. So it'll just find the larger of these two numbers. And so now you can call it, and this is something that changes. The amount comes in, and it calculates val equal to a global variable and adds the amount to it and returns that value. Right, so this is referring to a global variable defined on the previous page. And notice this uses a local variable called val, and this uses a local variable called val, and they do not collide. They don't stand for the same thing. Each one exists only within its own routine. So this is a separate variable that happens to have the same name, but it's not connected to the other one at all. All right, so local variables and parameters reside on the stack, which grows as needed. Stack frame is piled on top of stack frame every time you call a subroutine. The heap we'll talk about later for dynamically allocated memory, and these parts don't change during the running of a program. So you can have pointer variables. They contain an address instead of data. So here, if the variable p contains this address, then you go to that address and that's where the value is. And so you define an integer variable equals 10, and then int star p defines it as a pointer, and p equals ampersand var will dereference the variable, find the pointer to it, and put it in P. This is used all the time and real important to understand in C programming. Very often the source of confusion is understanding pointers. All right, so you declare a pointer variable with int star pointer. That means it's a pointer to an integer. It'll store the memory address of an integer, and this will store the memory address to a character variable. All right, so you initialize it by setting it equal to ampersand of something. This will point it to X. This will point that one to CH, as you can see here. All right, null is an invalid address. If you dereference a null pointer, you get an error message and your program stops. All right, so if you dereference a variable, you do it with the ampersand sign. So if X contains a pointer contains an address to X, then the star pointer contains the data there. All right, ampersand X is the address of X. Star pointer is the value stored at that location. That's how it works. Let me check the Twitch to see if there are comments. There are none. All right. So you define a couple of int star pointers at X and Y. You define X equals 8. Then you set pointer 2 to point there and pointer 1 to be null. So now pointer 2 points to X, which contains 8, and pointer 1 is null, so it doesn't go anywhere. So now you set pointer 2 equal to 10. This will store 10 in where pointer 2 points, which is X. Then Y is star pointer 2 plus 3. So Y is going to be the value here plus 3. So it's 13. Now I can set pointer 1 equal to pointer 2. That means both of them point to the same storage location. This happens, by the way, all the time by accident in Python. Very annoying. When you copy an array, you get two labels for the same array. You do not get two arrays. which has fooled me many times. Anyways, now you set star pointer 1 equal 100. That'll take this pointer, go to that address and put 100. There will also be changing what star pointer 2 is, since they both point to the same location. Now you can change pointer 1 to point to Y and put an 80 there, and now you've got this situation where each pointer points to a different variable. So just a little bit of stuff you can do to see how pointers work. And so here I assign a pointer an address of 20. That is almost certainly going to cause a crash, because every time you load a program, the operating system assigns it certain memory regions to use, and the low memory is reserved for the kernel. So these low numbers are never assigned to a user-land program. And so assigning a pointer to an arbitrary value is very likely going to cause your machine to stop, because you're probably not going to hit the part of memory that's allocated for that program. This is what you want. Star pointer is 20. That will take the address pointer equal to a variable. This will give it a variable in the region that's assigned to your program, and this will set that value to something. If you dereference a pointer variable that doesn't contain a valid address like this, you'll get a crash. Pointer is null, and you try to store something at that address. With star pointer, it's trying to store at null, and null is not a valid address, so that'll crash. Here you set it to 20 and try to store something there, and 20 is too low, so it's going to crash. Here you set it to a random value and try to store something there. This will almost always crash too, because the amount of memory assigned to your program is small. The amount of total memory is big, so the odds of hitting a valid memory location with a random number are very low. This is what you really want. Set the pointer to point to a real variable that you reserved space for, and then set star pointer equal to a value. That's how you point to an address that is in the memory you're allowed to use, and you write to that memory. And this is the kind of thing that happens if you don't understand pointers. All right, and so you can test for null pointers. You can just see if the pointer is null, and only do this if it's not null. You can control that instead of just letting your program crash. So let's try Kahoot. I've got them here. This is 2A, which will be here. All right. What's that? No, you don't need to make an account. Just go to that URL and put in that number. You can choose a name. Yep. Good. They may wish to join us. Good, we got 3 people. I'll give it a little bit more time and see if we get 4. All right, looks like that's what we get. All right, what part of memory contains local variables? It's the stack. Stack contains local variables, not the heap. And we'll see that when we get to the project later. You'll start doing stack buffer overflows to see exactly how it works. All right, where are the global variables? They're in the data section. They do not belong to any routine, so and if they're in the stack, they'd have to belong to the stack frame of one process, and if they were in the heap, they'd be temporary. The data is where you store them. They persist as long as the program is running. And how can you dereference a pointer? It's star pointer. Star pointer gives you the way to refer to the memory that pointer points to, and that's called dereferencing it. This would give you a pointer to the pointer, which you normally don't want. All right. Anyway, the 3 people, they all win. Good. All right. So let's carry on. All right, so pointers and functions, an issue here. So here you have a function to double a number. You have integer double number that takes a pointer to a value. This is the function declar prototype. Here's the actual function. In comes a pointer to an integer. It dereferences it and doubles it, and then returns nothing. So what this does is it doesn't return any value, but it changes this value, and since it has a pointer to the original data, it will change. And here's main just calling number is 5, before it's 5, call double number, and after it's 5. And so if you run it, before it's 5, but after it's 10. You can pass a pointer to a function, and then you're still manipulating the same variable as in the calling function. That's one way to return data from a function. All right, and that's the point here. Now, here's another one that won't work. Here the double number takes the value and then doubles it and returns. And the problem is this is just going to be a copy of the value. You pass it a 5, double of number of 5, it will make a copy of that value, double it, and then not return it, and not change the original variable, so it'll still be 5. This does some work, but it doesn't send the work back to the calling routine at all. All right. Let me check for comments in the Twitch. Aha, okay, nothing but spam. All right. So like I say, passing a pointer to a variable lets the function use the variable in the other routine. All right, and so we've already done things like that. You can change value. Here I'm going to call change value on a pointer to x. So when you go down there, it's going to change it by adding 100 to it or something, and that'll change it. Same thing as the one we've seen before. And so it'll have the address of x passed into change value. So when it changes it, it'll be changing the actual variable in the calling program. All right, and then so that's all local variables on the stack. Dynamic allocation is what you use if you want to allocate memory, use it, and then free it to reuse the same memory while running the same program. If you have some kind of temporary scratch pad need, that goes on the heap. That's what the heap is for. The heap is for chunks of data allocated for temporary use. So you call malloc to reserve some space, like the size of int. It'll return a pointer to that. So you define an integer pointer, p, you reserve something the size of an integer, and then you get a pointer p to it. Now you can use it, like star p equals 6. If it can't allocate memory, it'll return null. That would only happen when you run out of room on the heap. All right, so this is a good practice to check for that, although I often don't bother, but I write sloppy programs that tend to crash because I'm not writing commercial software. I'm writing hacking tools usually, and crashing is the least of my worries. Anyway, when malloc, if there's not enough heap memory, it'll return a null, so then you'll have an error and exit. This way you can handle the error this way, or you can just let it crash. All right, so when you're done using it, you can free it. That's the point. The reason you don't just put this stuff on the stack or as a global variable is because you're planning to only use it temporarily as a scratch pad. For example, you might have a program that processes network traffic. It'll take some network traffic, put it in temporary memory, do something with it, and then it's done. It can free that and put the next blob of network traffic on top of where it used to be. So that's the kind of thing. So when you're done, you're supposed to do these 2 steps, and this is one of the many reasons why C is a very insecure language. Every time you malloc something, when you're done, you have to call free and set the pointer to null. If you forget to do this, you leave a dangling pointer. P now points to memory that is no longer reserved for that purpose, but it's going to be used for some other purpose, and you can read and write data that you weren't supposed to be able to. And if you do this twice, you create another vulnerability. The second free can lead to a write operation you can use to take over the box. And in complicated code with many routines and with many different developers adding code and routines to it, it is very easy to lose track and not have exactly one free for every malloc. And that's what tends to happen. And one of the more common flaws caused, again, just C is full of booby traps. It's easy to make little mistakes that let people take over your program, and that's what we're going to do a little later. So you can have a dynamically allocated string. I've defined 20 integers, enough room for 20 integers here in this array. And here I've defined enough room for 10 characters. That's how you can reserve some space on the heap for arrays of data. And you can have pointers to heap memory and functions. So I have an address in the heap, and here's another address in the heap. So you can pass this pointer to a function. You could pass this pointer to a subroutine, and it could write to it, just like any other pointer. All right, let's try another Kahoot, which should go here. All right. So, all right, so which function will be able to modify the value of x in the calling program? This is the one. You pass in the pointer this way. The int star means x is a pointer to an integer variable. So you pass it in, I modify it, that'll change it in the calling program. All right, none of the rest of them work. This one in particular, someone chose, will certainly not work because you just pass in the value of x, it makes another copy of that value and adds one to it, but when it doesn't return it, so it will have no effect on what happens in the calling program. All right. When malloc fails, what happens? It returns null. Malloc returns a pointer to the reserved memory, and if it can't do it, it returns null. That's your clue that it failed. And what causes a dangling pointer? When you don't call free, you allocate reserved memory, and then you run on and don't call free, then you have a pointer to memory that's no longer being used for that purpose. All right. And the same 3 people, I reckon. That's all there are. Well, all right, so you can have arrays in C. We've already done it a bit. You can make a floating point array, a character array with this many points. These define them, and then you can access the elements. It starts at 0 and points up to the size -1. So you have, this will write something into the first 10 elements and put something in the first 10 elements of name. Now, characters, strings, have to end with a null byte. So you have to have an extra byte available to put a null byte in it. That's what a 0 looks like. That's null. And you can then print them out. You can print the third element of averages, names, and the whole name array itself. So an individual value in there is a floating point number, and you can use %G for that, or %F. %C is for a single character, and %S is for a string. So this will take the third letter and print it alone. This will take the whole string up to the null byte and print it as a string, and then put a carriage return. And here it's just going to copy hello into it and print it again. So when you look at the output, looks like I don't have the output here, but anyway, it tells you here what it's going to do. Anyway, all right, so that's what's going on. These are ways to refer to array elements. You can have a dynamically allocated array element where you assign them, declare them as pointers, and then use malloc to reserve space on the heap. And after that, you can use them the same way, although it's a good idea to check for null pointers. After that, you can read and write from them the same as you would any other array. But when you're done, you should free them and set them to null, so that if somebody tries to use them later, they won't be able to write somewhere in memory. All right, so your array is just a layout, 6 integers, each of which is 4 bytes. So the first one starts at one address, next one is 4 bytes later, 4 bytes later, 4 bytes later. That's what it is. It just lines them up one after the other, being whatever size an integer is, which is usually 4 bytes. And so, constants. You often define these. Define n to be 20, and then you refer to it here. There's 2 reasons to do this. One is it might be easier to read. The main thing is it's easier to update. If you make this for size 20 and then you decide I need to have size 50 later, you can just change one constant here to change them all. That's commonly why you use these things called a constant. These are processed before the program compiles. First it replaces all these constants with this value and then compiles. You can have a 2-dimensional array, but it's really just a 1-dimensional array in memory. It just means you store a certain number here and then the next row here and the next row here. So it's not really 2-dimensional in any physical sense, but it looks 2-dimensional to the programmer. All right. And then there's strings. Strings are a huge problem. The strings in C are not a series of printable characters like they should be, because they wrote it before anybody thought of any language but English, and they thought 1 byte is enough for a character, which is not true at all in this modern global world with a lot of languages. The correct strings are Python strings or Java strings, where you have a series of characters, and each character is a Unicode character that can go from 1 to 4 bytes. That's what a string really should be, but C strings are really just byte arrays. And that leads to a ton of problems, and we're going to exploit them right a little later. So I define 2 strings, or 2 arrays that can hold 10 characters. Now I can put in hi null, and that will print as hi. And I can copy one string to another. Stir copy is one of the many very unsafe functions. Stir copy will copy all the bytes from one string to another. So this will take string 1 and copy it to string 2. So string 2 will have hi null. Then I can set the second value to O, so this will be ho null. First one will be hi, the next one will be ho. Prints hi ho. So that's fine, and all this worked because I only used 3 bytes and I had enough room for 10. The problem is when you put in too much. So these functions are very dangerous because they start writing in a string pointer and they keep going until they hit a null byte, and they do not know how long the string is supposed to be. Now you might imagine that when you do the stir copy, the program will look back here and see how big the string is, but it doesn't. In general, it never does that. Assembly doesn't do that, and C doesn't do that. It only executes each command with no context. This is like the problems I mentioned with large language models. They don't understand what they're saying. So it doesn't ever know the context. So if you don't include a number right here that tells it how long the string is, it doesn't know how long it is. It will just copy until it hits a null byte. All right, so they don't check, and that's the problem. This leads to buffer overflows when you accidentally write too many bytes, and you can take over the box with them. We'll do it a little later. So they tried to make safer versions. String n copy is one where you add that length in there. String n copy, you add the length. So now you tell it how long it is, and it will therefore copy up to the first null or this many characters. So if people always use stir n copy instead and they filled in the length correctly, then there wouldn't be buffer overflows. Like most security solutions in C, this really just places more burden on the programmer, and they're more likely to make mistakes and fail to live up to it. That's the problem. But it does give you some degree of control. So here's a string of hello there. The length is 11. This is 11 bytes. There's an invisible, it's going to copy that in here. I made enough room for 32. There's going to be a null byte at the end. So now I'm going to allocate space on the heap for it and then copy my string into the heap string. But I'm only going to copy the first 5 bytes. And I'm going to explicitly add the terminating character. Since it starts at 0, the 5 bytes are 0, 1, 2, 3, and 4. Byte 5 is the 6th byte. I set it to null. That will terminate it. So that'll print, if you print string, stir here, that'll be hello there, and this will just be hello. I printed only part of it. And here I freed it, and notice they forgot to null it. You should null it too, but they didn't. Anyway, so stir L copy is a newer one that's supposed to be even safer. I've never used it, but it also copy up to the first 0 or size -1 characters, because the problem with the other one is it copies up to n characters, and then you need to add a null byte after that. So you could still accidentally write one too many. This one here avoids that. All right, so stir compare and stir n compare are big. Here's a irritating thing. If you define 2 strings and then you compare them with string 1 equals string 2, you're not comparing the string values, you're comparing the string pointers. This is a thing to understand. This, when you define a string up here, char stir 32, what you do is you define a string variable which is a pointer to where it starts, and then you reserve 32 bytes worth of memory. So the value stir itself is a pointer. So if you compare stir 1 to stir 2, you're comparing pointer stir 1 to pointer stir 2. You're seeing if they both point to the same memory location. If you actually want to compare the stored string byte by byte, you have to use string compare. This will go through the string. So here in string compare, we'll take 2 strings, it'll return 0 if they're the same, and a non-zero value if they're different. String n compare will compare them, but only up to the nth character. So here's an example. I put alligator in string and zebra in the heap string, and now I'm going to call string compare, and if it equals 0, they're the same, and so they're less than or greater than. And so this will be true for these strings, one is greater than the other. And but if I do string compare and compare only the first 3 characters, then I compare stir to the immediate string all. That's going to be alligator. The first 3 characters do match all, so this will be true. All right. So stir cat and stir n cat, these will combine 2 strings to make a longer string, like the cat command line command in Unix. So stir cat will take the source and add it to the end of the destination string. So it'll append these characters to there and then add a null byte to the end. So the destination string better be long enough to handle this plus whatever's being added to it. This is one of the many ways you end up with buffer overflows. And stir ncat will do the same thing, but you limit the size, how many bytes are copied, to try to give you some control to prevent the overflows. Stir will look for a substring in a string. Stir will look for a character in a string. sprintf is another one, very dangerous. You define a print statement, like here's a normal printf statement, % a string, end it with a carriage return. Now, I print the same thing. Here's the format string, here's the variables I'm printing, and you put it into a string instead of printing it on the screen. So again, the string has to be long enough to hold all this data, including the size of these variable values, which if you don't specify them, can be a variable length. So sprintf is another way to put data in a string. All right, like string copy. So there's also, for individual characters, you can find out if they're upper or alphabetic or digits or so on. And if they're space, these are available, although I don't know why you need them. But anyway, you can have those options if you want them. And here's some things to configure. This will convert a string to an integer, and this will convert a string to a float. Something else you might want to do if you, all right, those are useful sometimes. All right, but we'll play with that when we get to the assembler. Anyway, let's try another Kahoot. There's one advantage for showing up for class. You get these Kahoot points. All right. All right, so how many bytes will it take to store A after this declaration? Characters is just 10 bytes. Like I said, each character is just 1 byte in C, therefore it can really only handle English. All right, how many bytes would it take to store A after this declaration? Per character for integers, so you're going to need 40, not 10, and not 20. Each integer is typically 4 bytes long. All right. And which one of these is the safest function to use? That should be a T stir copy. Stir copy is the safe one. You get to specify the length. These others don't let you specify the length, so it's easy to overflow. All right. Anyway, I think it's the same 3 people. So, all right. So then there's structures. You can have other structures besides array. You can have something like a student where you have a name and an integer for an age and a floating GPA and another integer for a year. And that's one data item, and then you have an array of them. So you can copy the information. They're using a dot. So student1 dot name refers to this portion of it. Student1 dot age refers to that, and so on. So you can do that sort of thing. And the structures are just in that order. It'll have all these objects in order, being as big as they have to be, and then if you have an array of them, the next one will just be following right after it. And it'll be the same in the heap and the stack. All right, and then there's input-output. Standard in is standard input. This is Unix standards. This is standard input from the keyboard. Standard out is the screen. And standard error also goes to the screen, but it's an error channel treated differently than other output. And so printf writes to standard out, scanf reads from standard in, and standard error is where error messages go. So you can redirect them from the shell. This is not C, this is bash, command line Unix. So if I run a program called a.out, I can take the input from infile instead of from the keyboard with the less than sign. That's input redirection. So instead of typing in data, I'll first put the data in this infile and then run it from that file. Here I take the output and put it in out file. So instead of going to the screen, it'll go to this out file. Here, I can redirect standard out and standard error into a file called out file. That's what the ampersand does. It's going to do both the output and the error into here. And here it's going to redirect all 3 to different files. The input comes from in file, the standard out goes to out file, and the errors go to error file. So you can do all these things as you like. And this is commonly done. All right, so another way is to redirect standard out to one file and standard error to another. You can do it this way, command to out and 2 to error, because 0 is standard in, 1 is standard out, and 2 is standard error. You can redirect standard out to a file and then redirect standard error to standard out. That's what this does. This takes 2 and feeds it to channel 1. So it takes the standard error and puts it in the standard output, and then the standard output is redefined here. This is the most common form I see. I don't know why, but anyway. You can redirect both to a file, but not all files support this. That's what I thought. That's probably why. Bash and G shell support it, okay. But there are various Unix shells. Anyway, that's probably why this one is the standard one I see. That's the more generic one that always works. Anyway, so here's printf. I'm going to print some numbers, floating points, and integers. And then I'm going to print a string. So this will give me x is a decimal, x is 5, and y is a decimal, which is 10. This is going to give me a floating point, a tab, a string, a tab, and then a decimal, which is pi, hello, and y, and I defined pi to be 3.14, so I didn't use a math library which could feed in a constant, which would actually be pi to a huge precision. I just included my own approximation of pi here, 3.14. All right, and so like say %f and %g are for float or double. This is decimal. Here's unsigned characters, strings, pointers, and so on, and there are long versions of some of them, and even double long versions of some of them, if you define higher precision data. So numbers can be printed a lot of ways. Most commonly use decimal, but you can use octal or hexadecimal, and you can have unsigned, and you can have scientific notation where it's going to have the e, like 5 times 10 to the 7. It'd be 5e7. All right. And there's no formatting option to display a value in binary, which is annoying. That's something you might want. It's there in Python, but it's not in C. All right, so scanf reads from standard in, and the input values must be separated by white space. So here I'm going to read a decimal and a floating point, put it in these variables, and so when you type them in, you can just have them separated by spaces or tabs or any amount of white space. Doesn't matter. All right. Get char input character, read or write a single character. This will read one character from standard in, and this will put one character out to the screen. To do file input output, you declare a file variable, give it a name. These are pointers to files. Okay, call them handles, the in file and out file. Then you call open to open the program file for read mode. Then this will give you the pointer to it. So in file will be the pointer, the handle to that file, and your out file will be opening to write. So now you can use, you can read from this one and write to that one. You do them with, you could use put C, get C to pull characters in one by one, and put C to put them out one by one. That's one way to do it. The other way to do it is, that's how you close them. The other way I usually do it is with scanf, which should be coming here. Here we're doing characters again. Character-based reading and printing. String-based, you can do fgetS and fputS to read and write a whole string. I've never done that. What I normally do, this is the one I always used. fprintf prints to a file just like printf. That's the normal way to put data out. And the only difference is you have a file pointer at the start of it, a handle. Then you have the rest of the information you need to print. And it's fscanf to read from a file, just like scanf reads from the keyboard. That's all I ever used, was fprintf and fscanf. That's enough to do whatever you need to do. All right. And you can have an fscanf format string the same way as usual. %s will read a string up to the first white space, and so on. All right. And there are advanced C features. You can use argc and argv to have command line arguments in your program. This is the call in main for that, where you'd have something like this. You'd put in parameters, 10, 11, and 200, and it'll count all the items on the command line. You can do that. You can do that in Python too. Doesn't really matter too much to us here. We're not going to do that kind of stuff very much. But that's the point. argc is the count of arguments, and argv is the argument vector that contains every value, every argument followed by a null. So if a user enters this A out 10, 11, 200, argv will have these elements. argv0 will be A dot out, the first item on the line. argv1 will be the 10, 11, 200, and then a null. That's how it works. It treats the name of the program as one of the arguments in the argument vector. All right, converting data types, we talked about it before. This is alphabetical to integer, alphabetical to float. And you can do pointer arithmetic. This part is interesting. If I define a character variable called letters, and then I set them to null, this puts a null in there, okay. Then I can make the counterpoint to the first element. I can use a dereference the first element, and that'll be the pointer to it. That's one way to do it. So I initialize this pointer as null. I don't know why they did that, but you can. And here I set it equal to point to the first letter. This is one way. You could also set it equal to just letters, which is a pointer to the first letter. But here's the interesting part, pointer arithmetic. If you define a pointer, and then you add 1 to it, it's going to move by 1 data size, whatever the data is. If it's a character, it'll move by 1 byte. If it's an integer, it'll move by 4 bytes. which is not that obvious. That's what this does. Points to the next character address, next element. This is the next integer address, which is 4 bytes long. That's not obvious at all. Normally, plus plus would add 1 to the variable, but for pointers, it adds 1 of the pointer size, of the data size to it. All right. And so this will just show you that. If I have I++ here, and increment the pointers here, then they're each going to point to the next element. The letters will move up 1 letter at a time, and the numbers will move up 1 number at a time, even though the numbers have to move 4 bytes every time. It knows the size of them. And so you'll see this, letters go ABC and the numbers go 0, 3, 6, 9. It correctly understands this. Even though these are taking 4 bytes, 1 increment is enough to get to the next one. All right, that's enough of that. Let's take a look at the last Kahoot. But not that way, but this way. There. Good. All right, switch command will redirect standard input to a file. The first one, reads from the file instead of the keyboard. The less than sign redirects standard input. All right, where does printf write to? Standard output, that's where it goes. The screen. All right. And in this declaration, what variable contains the name of the executable file? It's the first element of the argument vector, which is argv0. All right. Same 3 people, so it's fine. All right. Oh, someone changed. All right. I'll do it. It's 9. All right. So, let me close this and stop the recording.